Hi, my name is Travis English, and I'm the Chief Design Engineer for Kaiser Permanente. I did a talk in 2016 about energy and M&V in our new buildings. I showed some data. I compared energy models to actual energy usage in 19 buildings, and the overall error, the inaccuracy in those energy models was 50%. So this is an update to that. These are buildings that we opened from 2014 out to 2021. So this is about 8 years worth of design and construction. And you can see the energy models that our designers did for ASHRAE 90.1 and for LEED. And the average inaccuracy or the error of this batch of buildings is 56%. Some of them are 100%, which means that the actual energy is double the model. And my first job here, my big job here, is to convince you that this is a problem that we should be working on. This is 56% error, and predicting a coin flip, of course, is 50% error. So an ASHRAE engineer doing an ASHRAE 90.1 energy model can call heads or tails with better accuracy than they can predict the energy in a building. And of course, predicting energy in a building is their job. So I think that's a problem. But I'd really, if you want to think about this in a very practical way, you think about this in an economic sense, in a payback analysis. If I have $1 million project with $100,000 a year in energy, well, that $100,000 a year in energy is actually a probability that spans between $100,000 and $200,000. So if an engineer comes to me and says, "Hey, look, if you spend 1.1 million, then the energy goes down to 80,000." And right now, most of us in the business would say, "Oh, wow, that's $20,000 in savings for a $100,000 investment. That's a 5-year payback. That's great, you know." But in reality, that $80,000 is a probability, which is, lands somewhere between 80,000 and 160,000. And at that point, the error is a bigger deal than the savings. If the baseline model was rooftop package units, for example, and the error on that might be just 10 or 15%. And if the savings proposal was something more nouveau, DOAS and chilled beams or something like that, then the error on that model could be 70 or 80%. In that case, the error would be bigger than the savings, and there's a very good likelihood that the energy saving system would cost more to operate and use more energy to operate. So we need to be concerned about accuracy. This is something that we've got to put our heads to. Now, my second job here is to convince you that we can solve the accuracy problem. And a big tool in that toolkit is connected commissioning and monitoring-based commissioning packages. With connected commissioning, what we're doing is we're taking building system data and connecting it to cloud-based diagnostics and making that data available to a wider audience. DDC controls are not new. We've had them for 25 years, but the data has always been locked up at the building where we can't use it. So the game changer with connected commissioning systems is accessibility. With a connected commissioning system, that the data from the building is on the cloud, which means that on day one, when the building opens, our design engineer can be looking at the data and the diagnostics, from their house in their underwear. And it's going to be a process. I'm not going to lie. If you're a design engineer, the first time you use a connected commissioning system to validate a building, it is going to hurt. And I mean, it actually hurts. Egos are shattered and just left in pieces on the floor. And the second and the third times that you use a connected commissioning system to validate a building, it still hurts. It still hurts badly. But if we do this regularly, day after day, building after building, it gets better. We learn, assumptions can get updated, and things get better little by little. One building, this is not going to do it, but generation after generation of designs, we can absolutely move towards accuracy. Okay, so if you've never seen an energy model, this is what they look like. Sometime in early design, the design engineer puts out a report. It kind of looks like this. Here's the ASHRAE baselines, 58 kBTU per square foot per year, 45 kBTU per square foot per year. Hey, there's the Kaiser energy target, 50 kBTU per square foot per year. And they say, look, our building is going to do 39 kBTU per square foot per year, right? But What I want you to really notice here are the colors, because an energy model is not just one energy estimate. What the models are doing is they're estimating each type of energy use and then adding them up. So the teal color is for fans. The red color is for heating. The blue color is for space cooling. Each one of those is a discrete calculation. And that's important because there can be error in each calculation. You can overestimate one and underestimate the other, and you might come out at 39 kBTU per square foot per year. But that's actually not what we want, because that's still inaccurate, right? We want accuracy in the calculations. And the other thing to know is that these are not annual calculations. Anytime somebody hands you a number that's in energy units per year, those calculations are actually done per hour, and then they're summed up. So somewhere behind the curtain, there's a piece of software that runs 8,760 hourly calculations, then piles up the results. That is also super important, because we used to talk about measurement and verification and doing measurement and verification at the end of the first year. You do not have to wait a year to validate your design calculations. You only have to wait 1 hour. So if your building opens tomorrow at noon, you can check your design calculations tomorrow at 1 p.m. We always ask the energy modelers for those 80,070 line spreadsheets, 8760 line spreadsheets, but we don't always get it. If you don't get it, that's okay. You can always take the individual numbers and the buckets and break them down into monthly and hourly numbers. I'm going to talk about fan power for the next couple of slides here. So in this building, we have an annual number for fan power that's based on about 300 hours per month. And so you can break it down, divide by the size of the building, and it comes up to 0.3 watts per square foot hourly average. So put a pin in that number, write it down on a napkin or something, 0.3 watts per square foot. If you have the model, then you can look at the fan power in each hour. We like to plot it like this. Outside air temperature is on the x-axis and watts per square foot of fan power is on the y-axis. This is a different building, by the way, but you can see from 0.2 to 0.3 watts per square foot of fan power, you know, most of the points are falling in that range. By the way, if you opened this building tomorrow at noon and you looked at it at 1 p.m. and it was using 0.4 watts per square foot of fan power, you could fail the building immediately in the first hour, right? That's what we mean by you don't have to wait a year. Okay, so let's look at some real data. This is 1 year's worth of data, and it's for that building that you just saw the model for. And the results are very, very pretty. You can see that data lining up at 0.2 to 0.25 watts per square foot. It's actually less than the model. And we'd say, oh, that's great. You know, the heavy line in the middle there is the one to really look at. That's the average fan power for all of the hours at the temperature range that's on the x-axis. Those light gray lines above and below are the 10% and 1% lines, right? So that's what we want it to look like. Let me show you another one. This is a building that's in commissioning right now. The data that you're looking at goes from August 8th to September 11th, and the fan power is looking between 0.6 and 0.8 all the way up to 0.9. This building is officially open. I think ribbon cutting is done. I don't think that they've seen their first patient yet, but that doesn't matter. If the building does not need to be occupied, don't fall for that. We actually fell for that in the early days. We had an engineer and a commissioning guy say, oh, this building really needs to be occupied and have some load in it before it'll start working according to the design. Words to the wise, do not fall for that. This building right here is using 3 to 4 times the fan power compared to its design, and bringing people into the building is never going to help that problem, right? Show another example to talk about a couple of things, 3 or 4 things. This was a building in Hawaii. It's open, it's 50% over its energy model. And in this case, we did not have a fan power point in the control system. So by the way, that's thing number 1. If you want to validate fan power, please put the fan power point in your controls. In this case, we did have CFM points on all the air handlers, and we were able to extract the airflows out of the energy modelers. So what you're looking at here is airflow in CFM for each of 4 air handlers. The bottom line, the lower line is showing the modeled CFM, and then the top line is showing the actual CFM. And I want to point out a couple things. First, I'd like you to look at the width of each one of these days. Our energy modelers often assume that we're going to run from 8 a.m. to 5 p.m. In our buildings, that's almost always wrong. Most of our buildings start up at 5 o'clock or 6 o'clock in the morning. And then we do run them past 5 p.m. We leave the fans on for the cleaning crew so they can run till 7:30 or 8. That's important because that's the difference between 200 hours a month and 300 hours a month of fan power. The second thing to look at is the actual shape of the curve. This energy model assumed a profile where there's a peak and then there's kind of a rapid drop off in the next 2 hours. And that is pretty much universally wrong for all of these air handlers. Those afternoon airflows after 3 p.m. are staying high. So even if these lines were at the same level, the shape of the curve, the plateau, we would incur more fan power. The third thing to look at is the spike that you see in every morning on every air handler. That spike is not a mistake. It is part of the design. That's the morning warm-up sequence. It's on the plans, it's in the specs, it is 100% part of the design. It is 100% not part of the energy model. And so that's inaccurate. If we're going to have a spike every morning in the design, we should have a spike every morning in our calculation. It's going to do that 260 mornings per year, by the way. That's 260 hours per year that will be at full power. That's like adding an extra month to the fan power. And then finally, we'll talk about the levels. You can see on the third run down is RTU3, and we had already found the issue. What's happening here is that we had a model that said that these units would run down at 4,000 to 4,500 CFM, but if you were to go into the building and put every zone to its minimum position, the sum of the minimums on the zones was 6,000 or 8,000 CFM. Well, the unit can't turn down to 4,000 CFM when the zones are calling for 6,000 or 8,000 minimum, can it? And so what my engineer had started to do was to go out zone by zone and start knocking those minimums down here. I hope you kind of see the big picture here. There's actually nothing mind-blowing or unpredictable here. There's nothing that we couldn't get right if we tried to get right in our energy models. It's just a matter of getting these things right and moving towards a more accurate way of calculating. Okay, let's move off of fan power. I know we're all HVAC guys, so we want to talk about cooling. Let's talk about cooling. So this is the same slide that I showed you earlier, just to kind of break down a cooling number into an hourly number. So this is a cooling number. We divide it out and we look at an annual average hourly number of 0.8 watts per square foot. So put that number in your head for the next 5 minutes, write it down on your napkin, 0.8 watts per square foot. Okay. Here's some real data, same building that I showed you before. This is 1 year of historical data for cooling in one of our clinical buildings. Now, the unit thing is a problem. I grew up as a square foot per ton person. One of my engineers grew up using BTU per square foot, so we find ourselves always converting back and forth. So in this case, the installed capacity was 35 BTU per square foot, which is 330 square foot per tons. That's how big the units are. Now, in the 95-degree historical data, we did have 10% and 1% of the data that got up to about 22.5 BTU per square foot or 550 square foot per ton. But the average at the 95-degree day is 17.5 BTU per square foot or 700 square foot per ton. That's where we're actually at in the 95 hour. And that's about half of the installed capacity. So compared to the historical load, the unit is basically oversized by double. And I'm going to talk more about that in a minute. But I want to say at this slide that we're talking about energy. And it may seem that we're overly focused on energy, but I want to be clear, not everything here is about energy. Even when you're talking about energy, it's not just about energy, right? This is about design. A unit that's double sized is a design problem. That's about cost. It's about supplier temperature control. It's about short cycling. It's about service life. We use the energy numbers to talk about these things, but we're really talking a lot about design. Okay. So what does that look like in watts per square foot? Remember the number that we had in our head was 0.8 watts per square foot. So to convert the load to the energy, you use EER. The units on EER are BTU per watt. So if we assume a 9.0 EER on this cooling load, we can see where that comes in. And that 0.8 watts per square foot number that you have written down on your napkin means that we should be tracking somewhere in the neighborhood of 7.5 BTU per square foot or 1,500 square foot per ton as kind of our annual average, which is pretty good, right? That number's pretty good. So here's a hospital. I come from Kaiser. Everybody wants to see a hospital data. This is the hospital. This is the hospital chiller system. The hospital does see some higher loads in it when we got up over 25 BTU per square foot, you know, in the 90-degree hours. But the sizing also went up here. In this case, the engineer sized the chillers. There are 2 chillers at 45 BTU per square foot. And then, of course, we have an N+1 chiller. So the total plant capacity is 70 BTU per square foot. And we're not really sure if we think we've fired the second chiller, but I don't think we've ever actually needed the second chiller, right? So what's going on with this oversizing thing, right? It's almost a cliche, by the way, to say that HVAC engineers oversize the cooling by double. What's actually going on with that? Like, what the hell is actually going on with that? So again, let's look at the data. This is a nice big data project that we did last year. We literally went into every zone in one building and looked at the historical cooling load in every hour of the year. We actually started off with one building and then we ended up adding 3 more buildings. So it's a lot of data. And we did publish this paper through ASHRAE with the peer review and all that. So you could buy it from ASHRAE. You don't need to. You go to YouTube and you type in historical HVAC cooling loads in typical hospital spaces, and it'll pop up. More than anything else, I want to communicate that this is possible. So our point in publishing this wasn't so much to say, hey, these are the historical loads, use them, although that is true. But the real point here is that with cloud-based diagnostic systems, we can look at historical loads in any building, any day, any year, and we should be doing that. We should be doing that every day, really. To summarize this, on this slide, what you'll see is that we actually found the room peak loads in our ASHRAE style load calculations are pretty good. So in a patient room, the design engineer is going to calculate 30 BTU per square foot, and that's about what we found. At some point in the year, that room is going to peak out at 30 BTU per square foot. However, and you knew that I was going to say however, and this is the important part. When we do load calculations, we always assume that similar function rooms are going to peak at the same time. In reality, that is never true. So I had one of those dads that told me, don't say always or never. So I'm doing this very carefully. Let me repeat that. When we do load calculations, we always assume that similar function rooms peak at the same time. In reality, that is never true. So if you take a look at the top line here, the peak in an office room or zone is 38 BTU per square foot. But when you look at 20 office zones together, the maximum simultaneously occurring peak is 5.5 BTU per square foot. That's a diversity factor of 15%. So you look at those columns, or 85%, whichever way you want to look at that. So you look at those columns over on the right. Anytime you have more than 5 rooms or 10 rooms or 15 rooms of the same type on the same system, you should be figuring a room-to-room diversity. And to my knowledge, nobody's doing this. And it's a big deal. This may not be the only reason that we're oversizing cooling systems by a factor of 2, but this is a big reason why we're oversizing loads by a factor of 2. And again, this isn't really an energy topic. This is a design topic, right? This is about air handling sizing. This is fan sizing. This is shaft sizing. This is pressure sizing. This is static regain. This is about controls, right? There's a lot to be unpacked here when you're oversizing units by double, right? Okay. Let's go back to this slide. This is the opening slide that I showed. The energy models are off by 50%. You can flip a coin and get better accuracy. You remember that joke? So we'll go a little bit deeper on this. What we found in our energy models is that natural gas is a particularly bad calculation. The energy model gives us electricity and then it gives us natural gas and it puts those in separate buckets. But if you isolate the natural gas, the inaccuracy or the error that you find is much higher. So across these buildings, the average error is 150%. And in the worst case, it's off by 435%, which is a factor of 5. So it's not at all uncommon for us to open a building and to see natural gas in the first couple of months that's off by a factor of 2 or 3 times the model. So let's get into this. And before we dive too deep here, let me mention that domestic water heating, the next 5 slides I'm going to show you are BTU per square foot numbers. But somebody in the room would raise their hand and say, hey, domestic water heating is part of the natural gas number 2. Yeah, that's true. But the most conservative estimates you'll find for domestic water use are 0.5 BTU per square foot to 1 BTU per square foot during the occupied hours. So bear that in mind. In most cases, it's actually a negligible number to the overall count. Okay, so how does this actually go down? Let's look at an example. In this building, our design engineer does a calculation. The ASHRAE heating calculation comes up at 15 BTU per square foot. That is a by the book ASHRAE heating load calc. Now, everybody's going to add a safety factor to that. So they add a safety factor to that and they install the boiler at 21 BTU per square foot. Of course, this is a fully redundant system. So we actually installed 42 BTU per square foot of heating capacity. Okay, so here's the loads. We had a few hours in the year where we got to 9 BTU per square foot, but the real number that you should be looking at is that average load. So when we're in the 40s, that number is about 7 BTU per square foot. So the load calculation, the ASHRAE load calculation is over by a factor of 2. And then more importantly, this boiler is installed at 21 BTU per square foot, and we're spending a whole lot of time in the system down at 2 BTU per square foot. Now, there's probably somebody in the room who says, well, we have boilers that do 10 to 1 turn down or 12 to 1 turn down. They're actually more efficient at the low range than they are at full load, right? Well, that would be great if that were true. So let's go ahead and check that. And we'll use the data to check that. Because when you have a data system, you can sum up the load in every hour of the system during the year. That means that you can sum up the load for every hour in the system in a month, and then compare that to the natural gas bill that you paid for that month. And that gives you the system efficiency. In this case, looking at a couple of months, the system efficiency was 58%. I want to make sure everyone understands this. System efficiency is very different from equipment efficiency. You can specify a 90% efficient boiler, but there's also the pumping and the piping and the valving and the gas trains and the flues and the cycling and all these other things that contribute to system efficiency. And system efficiency has to be the overall goal. Yeah? I told you that story, so I could tell you this story, because this is the worst one we've ever seen. And I made sure that you can't read the name of the boiler manufacturer here, but suffice to say, this is the most expensive boiler that money can buy. This is a 94% efficient steel tube condensing boiler, right? And right away, we opened this building. In the first 2 months, we could tell the natural gas was way off. So we checked it for December and January of the first year of operation. This is the winter time, brand new building, brand new boiler, 94% efficient, most expensive boiler money can buy. The system efficiency was 30%. So I kind of love this report because it teaches the valuable lesson. Design engineers are sometimes fooled by this notion, hey, if I specify a 94% efficient boiler, then I'm done. And that is 100% false. I hate this report because I own this building. And the problem here is you can't fix it. You can't fix it at the boiler plant. Delta T can never be solved at the boiler plant. System flow can never be solved at the boiler plant. The temperatures, flow rates, minimum flow rates, pump sizing, pipe sizing, bypass GPM, coils. In this project, all of that was wrong. And so this actually isn't about the boiler at all. This is about the system. This is a bad hydronic system design. And this isn't about energy, really. This is about design. The design of that hydronic system is poor, right? So the overriding idea that we've come to here is that if you're going to hit an annual energy target, that means that you need to hit your hourly energy targets about 8,760 hours in a row. So we might show our calculations to USGBC or the Energy Commission or the owner in units of per year. But what we need to do on the ground during commissioning and during startup is to validate those performance metrics in units of per hour. So the hour is the all important unit when it comes to validating our systems. And what we started to do about 4 years ago is this. We've started to require acceptance criteria from our design engineers during design. We say to put them on the plans for system validation. What should the data look like on day one when we fire up the system? Put that on the plans where everyone can see it, and we know if it passes or fails during commissioning. And we've come to find out, or we've discovered, that there are about 4 categories of acceptance criteria. There's systems in control, turn up, turn down, efficiency, and then there's what we call the non-trended points that are more binary in nature. So as an example, if we have a boiler, first we would want to see that the system is in control. Temperatures are in control, pressures are in control, delta T is in control, flows are in control. That's what we call systems in control, right? And that is a prerequisite to anything else. Do not start working on energy efficiency if your system is not in control, right? Next, we should see turn up and turn down. So is it shutting off at night? Is it turning on during the day? Is it ramping up when it's cold out? Is it ramping down when it's hot out? And then we would look at efficiency. We look at the BTUs in the heating loop. We divide those by the BTUs in the gas train. And we want to see that number better than 80% every single day, starting at day one. And then there are the some yes or no, check the box type of points like failure modes. For electrical systems, we tend to have a lot of these non-trended points. Yeah. And so we tell the engineer to put them on the plans. So this is an example. This is the acceptance criteria put right on the plans. You probably can't read this, but I hope you can see that these charts for fan power and heating power and cooling power are right there on the plans at different outside air temperatures to show what we expect to see. This gives our commissioning team what they need to go out there and validate these systems. And that plus a good controls design, I should say. I think I already said, if you want to check the fan power, you have to put a fan power point in your controls. If you want to check the cooling power, you have to put the cooling power point in your controls, right? The other thing that I'll point out here, you'll notice that on this sheet of plans, there are 2 professional engineer stamps. We did make a decision about 2 years ago that our commissioning agents need to stamp and sign the controls plans. We don't want them writing comments about the controls plans. We want them to stamp and sign the controls plans. That was kind of a controversial decision about 2 years ago when we made it. I think that controversy has more or less, fallen off. But these acceptance criteria, the point here is that these acceptance criteria make things objective. They make things numeric. We're not going to accept the building because the design engineer saw the fan spinning and thinks that they're working right. Or we're not going to decline the building. We're not going to hold the building up because the commissioning agent thinks that the VAB is off. We're going to accept the system when the fan power is below 0.3 watts a square foot. And we're not going to accept the building until the fan power is below 0.3 watts a square foot, right? And where we're going in the future with this, and by the future, I mean the system, the plans that are in design right now, is that these criteria that you put on the plans during design also become the continuous criteria for operations in the life of the building. So you don't have to write a separate document that's the measurement and verification plan or a continuous commissioning plan, that this is the measurement and verification plan, and it's right here and it's on the plans. So kind of talking to my boss and my team in the last few weeks, this is where I think we're going as an owner. We do have to check the equipment to make sure that it can actually achieve a lot of the turn downs that are necessary in the system and that it's actually sized appropriately for the system, right? So if you're thinking about installing a boiler that's more than 5 BTU per square foot, that means you're never going to achieve the turn down that you need. So stop right there. We need to talk about that. If you're thinking of installing air handlers that are bigger than 0.7 CFM per square foot, then stop. You've clearly done something incorrectly with your load calculations. We need to talk about that. If you're thinking about installing cooling that's larger than 20 BTU a square foot, then just stop, right? There's something off about your load caps, and we need to talk about that. And we know that those systems are not actually going to make it when it comes to turning down and doing things appropriately. So to come back to this slide, I hope everybody's seen a slide like this, right? Plan, do, check, act. It's one of these virtuous cycles. And I'll go ahead and repeat. The first time you use connected commissioning to validate a building, it's going to hurt because you're going to see all the things that you assumed in your design that are just not true in the actual building. But if we do this enough, if we do this day by day, building after building, then it gets better. We can learn and the assumptions get updated and things get better little by little. So let's talk about ASHRAE Standard 100. Probably a lot of people here haven't heard of ASHRAE Standard 100, but this is a standard for energy efficiency in existing buildings. It is otherwise known as a building performance standard, or BPS. So if you hear about building performance standards, BPSs, that's what this is. The reason that I'm thinking about ASHRAE 100 is that there are already jurisdictions that are adopting either ASHRAE 100 or some modified targets based on ASHRAE 100. Boston, Denver, Maryland, New York, Reno, St. Louis, Colorado, state of Washington, right? And I don't want to lean too heavy on my crystal ball here because crystal can break, but sitting in California, you have to sit here and think, how long is it going to be before the California Energy Commission starts to look at something like this? So this is what ASHRAE 100 actually looks like if you open it up and read it. And the two climate zones that I have highlighted there are climate zone 5B is Denver and climate zone 4C is the Pacific Northwest, which includes Portland and Seattle. For a medical office building under ASHRAE 100, the EUI target is around 30 kBTU per square foot per year, 34, 36, 28, 20. You see, those are the numbers, right? Now, both Denver and Washington have adopted higher targets. In Washington, they adopted 100, but you got to be there by 2025. And in Denver, they adopted 65, but you got to be there by 2024, just 2 years away. And then, of course, in Washington, they're talking about dropping that 1% per year after that. So these are the buildings that we own in those regions, right? These are the buildings, and these are not the legacy buildings. These are the buildings that have been opened in the last decade. So the boilers, chillers, rooftop units, controls, all less than 10 years old in these buildings. In Washington, we're actually in pretty good shape because they adopted that higher target, right? They adopted 100 EUI. If they were to adopt ASHRAE 100, which is the little blue line at 30 EUI down there, we would be in a world of hurt. In Denver, they've adopted a lower target and we're already in some hurt. And we only have one building that meets the target and we've got 2 years to get everything else to that target. So we've got buildings in this portfolio that are less than 10 years old that are double the energy targets they need to be at by 2024. Those are going to need at a minimum a serious HVAC overhaul. So this is what I mean by accuracy is going to matter, right? If we start to get into building performance standards like this, and by the way, this is a decarbonization topic. The Decarbonization Task Force is working on this. But as we get into these BPSs, then that accuracy matters. And my crystal ball says that this is where we're going. We're going to move away from that 90.1 and LEED paradigm where we say, oh, our design is 40% better than the standard. I think everybody at this point knows that that's kind of bullshit. And so these hard numbers are where we're going. So before I close this up, if you're a design engineer thinking about this, let me give you a scenario. And I think this is a plausible scenario. Let's say that you're an energy modeler. You've designed a building in Denver, Colorado, and it's going to open in the year 2023. You did your energy model. It's 30% better than 90.1. You got your LEED plaque. You've already posted it on your wall. All's good on that department. Then the building opens, and its year one energy is 100 EUI. Now you need a 45% reduction by year 2 in order to meet that target. The first thing the owner is going to do is an audit. And the audit will show that they need to invest $1 million in the HVAC system in order to reach the target. To me, that's an open and shut case of design liability. And I think that owner should think about suing the design engineer to pay for what it takes to meet the code. This is a brand new building that you said was going to be energy efficient, and here it is not energy efficient. Now, maybe you agree, maybe you disagree, maybe you're a design engineer and you want to talk to your lawyer about it or something like that. That's not the point. The point is, if we're doing calculations and publishing numbers, we have a responsibility to make them as accurate as we can. We've actually dodged that responsibility for a lot of years, and it's definitely time to start making up some ground. So we need accurate calculations. In order to improve the accuracy of our calculations, we need to use the data. The good news is there's lots of data that is now available for us to look at. We live in an era where data is more available and accessible than it's ever been. We need to turn our attention to that data and use it to improve the accuracy of what we do.